Hello, statistics and pre-calculus. So we are going to jump right into an exponential growth word problem. How do we do its growth? Well, we have this lovely word growth in our problem. So the first question is, we have a small town that has 15,000 people in it as of 2001. We want to know, in 2016, after the population has grown to 34,000, what was the average rate of population growth over that time? So remember, first thing we want to do, remember our exponential growth formula. Y equals A times 1 plus R raised to the, where Y is where we end, A is where we start, R is our rate of change, and T is time. So, in this case, we have to find out first, what are we solving for? So, it asks us, what is the average rate of population growth? That means that what we are solving for is R. That's the thing we don't have. Since we only have one equation, and we already have one unknown, we must have all of the other pieces, right? So let's just go ahead and get into it. So, our Y is where we end. So it says we start with 15,000 in 2001. We end in 2016 with 34,000. That means that our Y is 34,000. And our start, A, is 15,000. So we just leave this as 1 plus R, because remember, R is what we're looking for. We don't have it yet. And then we need to find T. So we actually have T. It's not given to us explicitly, but we can figure it out. So T is going to equal the end date minus the start date. So the number of years that have passed between these two years is 15. 2016 minus 2011 is 15 years. So this is how we set up our formula, right? So at this point, we can solve this a couple of different ways. So our first way we can solve this is by kind of using our cheat way, which is plugging it into the solve function on our calculator and telling it to give us the answer, right? Which we could do here. Maybe we'll do that as a check. But let's actually figure out how to do this logically, right? How to solve it algebraically. So that means we're trying to isolate this R here. So first thing we're going to do, divide by 15,000 on both sides. And that leaves us with 34 divided by 15 equals, let's just round up, we're going to say that is equal to 2.267 equals 1 plus R, still don't know R, to the 15th. How do we get rid of this 15? So, if this was squared, we would take the square root, right? If this were cubed, we would take the cube root. In this case, it's 15th, so we're actually going to take the 15th root of both sides. So we're going to have the 15th root of this guy here equals 1 plus R. So we're going to go ahead and either do that, or you can raise this to the, so the 15th root is also equivalent to 2.267 raised to the 1/15th. Equals 1 plus R. Either one of these is going to give us the same answer, right? Go ahead and type that in my calculator. I get 1.05607 equals 1 plus R. Last step is, of course, subtract from 1 on both sides, and I'm left with R equals 0.056, or R equals 5.6%. So, oops, missed that last one. So this is our final answer, right? Now we have R. We did that without using the solve function, so we actually solved that ourselves. And again, we can check on our calculator, right? We can plug this back in to solve, make sure we got it right. So, next step. Once we have R, this problem asks a second problem, right? So same general question, or same general situation, but we have a new question now, right? So now we have the population growth rate is constant, right? So that means that we're going to be using this R equals 5.6% number that we just found. And it's asking us, what year did the population reach 25,000? Or when, right? And remember, if we hear the word when in a word problem, that means we're solving for time, right? So we already know t is what we're solving for, so we got to plug in everything else. So our y, where we end, again, is going to be 34,000. 15,000 is our start, and our end is 25,000 this time, right? Because we're given a new end. That's what changes. 15,000 is still our start. We get 1 plus r, so the r we found in the first problem, 0.056, all raised to the t. So in this case, t is the variable we don't know. That's what we're solving for. So once again, we can solve in our calculator, but now that you guys understand logarithms a little better, you should also know that we can solve this using our log function, right? So once again, very first thing we want to do, we want to isolate our t, right? So we're going to divide both sides by 15,000. We should get 25 divided by 15 equals 5/3. We'll just leave it in that fraction. That's a nice fraction. 5/3 equals 1 plus 0.056 to the t, right? So this is where we get a little tricky, right? So remember that log base b of our answer is our exponent, right? This is also the same thing as saying your base b raised to an exponent equals your answer. So in this case, we're in this form, right? And we want to rewrite it in this form. So in this form, where we are right now, our base is actually 1 plus 0.056, or 1.056. Our exponent is t, and our answer is 5/3, right? So when we rewrite this guy, we're actually going to have, sorry, let me move this down. We're going to have log of our base. Remember we said our base is this little guy here. So log base 1.056 of our answer. Our answer we said is 5/3 equals our exponent t. So make sure you're comfortable with writing it like that, right? So we just rearranged this guy. We went from our base exponent form to our log base answer form, right? And at this point, we plug this into a calculator. So what we do at this point is we just type this guy, log base 1.056 of 5/3, into our calculator, and our calculator spits out that our answer is t equals 9.37 years. So at this point, this is actually not our final answer, right? We have to go back to what did the problem ask us for? Our problem asked us for not when in number of years, but what year, right? So remember back in our first part, we were told that this start time, or the start population 15,000 was in 2001, right? So it gets to 25,000, 9.37 years after 2001, right? So 2001 plus 9.37, right? We don't really talk about years in decimals, though. So what we can really say is 2001 plus 9, so sometime during 2010, right? Not at the start of 2010, but sometime during the year 2010, our population reached 25,000. Alright, so this was your exponential growth problem. Next we're going to do an exponential decay problem.